Hello everyone, this is Dr. A classes for BTech students. Igneous rocks formed through the solidification of molten material provide essential insights into geological processes. This lesson explores their origin, formation mechanism, and key characteristics, laying the foundation for understanding their role in engineering applications. As a fundamental component of petrology, igneous rocks are integral to engineering geology. Their composition, texture, and structural properties help civil engineers assess material suitability and site conditions, ensuring stability and durability in construction projects. Learning objectives of the course is describing the formation processes of igneous rocks, including crystallization from magma and lava, distinguishing between intrusive and extrusive igneous rocks based on cooling environment and texture, classifying igneous rocks based on their mode of occurrence, chemical and mineral composition, interpreting petrological data to assess material suitability and stability in civil engineering, assessing the suitability of various igneous rock types for construction material, including aggregate and foundation rock, evaluating the impact of igneous rock properties on tunneling, dam construction, and other civil engineering applications. What is an igneous rock? The term igneous is derived from the Latin word ignis, which means fire. Igneous rocks form when molten material known as magma beneath the surface or lava on the surface cools and solidifies. Because they originate from the intense heat deep within the earth, these rocks are often called fire-born. They make up the foundation of Earth's crust and are considered the primary or the parent rocks in the rock cycle, from which other rock types eventually develop. What is magma or lava? Magma is molten rock trapped beneath the Earth's surface, rich in dissolved gases and crystals, stored under high pressure and temperature that ranges between 700 to 1300 degrees Celsius. As it cools slowly underground, it forms coarse-grained intrusive rocks like granite. When magma reaches the surface through a volcanic eruption, it's called lava. It loses most of its gases, is exposed to much lower pressure, and cools rapidly to produce fine-grained extrusive rock such as basalt. Composition of magma. Magma, the molten material beneath Earth's crust, is a dynamic mixture of elements and gases. Silicon and oxygen dominate its composition, forming the framework for silicate minerals, while metals like iron and magnesium influences rock strength and coloration. The presence of volatiles like water vapor and carbon dioxide affects magma fluidity and eruption style. Depending on the silica content, magmas are categorized into felsic, intermediate, mafic, and ultramafic types. This classification influences key characteristics such as viscosity, eruption dynamics, and the resulting igneous rock's composition. Solidification of magma into igneous rock. As magma cools, it undergoes crystallization, where minerals form in a specific order dictated by Bond's reaction series. This sequence explains why certain minerals appear together in igneous rocks. The rate of cooling has a major influence on the texture of the resulting rock. Intrusive rocks form underground and cool slowly, allowing large crystals to grow, producing coarse-grained rock like granite. In contrast, extrusive rocks cool rapidly at or near the surface, resulting in fine-grained or glassy rocks like basalt or obsidian. From an engineering perspective, the formation environment affects rock properties such as compressive strength, weathering behavior, and suitability for construction. For example, coarse-grained rocks are typically more durable and easier to evaluate for load-bearing applications. Classification of igneous rocks. There are three major criteria used to classify igneous rocks. Understanding these classification is fundamental in geology and especially important in engineering applications. The three key criteria are mode of occurrence, where and how the rock forms, chemical composition, mainly based on the silica content, mineral composition, determined by the types of mineral present in the rock. Each of these criteria affects the texture, color, strength, and durability of the rock, factors that are critical when selecting materials or assessing site condition in civil engineering. We will now explore each classification in detail in the following slides. Classification by mode of occurrence. Here we will discuss how igneous rocks are classified based on their mode of occurrence, meaning where the molten material cools and solidifies. Extrusive or volcanic rocks form when lava erupts onto the Earth's surface and cools quickly. The name volcanic is derived from Vulcan, the Roman god of fire, representing their fiery origin above ground. In contrast, intrusive or plutonic rocks form when magma cools slowly within the Earth's crust. Because the cooling is slow, these rocks typically have coarse grains. The term plutonic comes from Pluto, the Roman god of underworld, symbolizing their formation deep underground. Understanding this classification is important because it influences the rock's texture, strength, and engineering properties. Extrusive or volcanic rocks. Extrusive rocks are formed when molten magma erupts onto the surface and cools rapidly. Because of the fast cooling rate ranging from few seconds to days, there is little to no time for large crystals to form. As a result, these rocks typically have a fine-grained, aphanitic texture, or they may appear glassy or vesicular containing gas bubbles. Common examples of such rock types are basalt, rhyolite, andesite, obsidian, pumice, and scoria. Intrusive or plutonic rocks. Intrusive igneous rocks, which are formed when magma cools and solidifies deep within the Earth's crust. The surrounding solid rock, known as country rock, insulates the magma, causing it to cool slowly over a long period. This slow cooling allows large crystals to grow, resulting in coarse-grained texture that is visibly crystalline. Intrusive rocks are not only classified by their mineral composition and texture, but also by the shape and size of intrusion and how it interacts with surrounding rock layers. Common types of intrusive formations include batholith, stalk, laccolith, sills, and dikes, each with distinct geometries and formation processes. This fundamental knowledge is essential for understanding subsurface geologic processes and rock identification. Classification by chemical composition. Igneous rocks are chemically classified primarily based on their silica content, which greatly influences their mineral composition and texture. The first method divides rock into acid, having more than 66% silica, intermediate, having silica between 55 to 66%, basic, consisting of silica between 44 to 55%, and ultra basic, having silica less than 44%. But it's important to understand that these boundaries are somewhat arbitrary and not always reflective of the actual mineralogy. A more rational classification considers whether the rock is supersaturated, saturated, or unsaturated with respect to silica. This system provides better mineralogical insight and avoids rigid boundaries. For instance, supersaturated rocks crystallizes free quartz, while undersaturated rocks may contain minerals like nepheline or olivine, which form only in silica-poor environments. This classification helps in predicting the rock's behavior, stability, and uses in civil and geological engineering contexts. Classification by mineral composition. The mineralogical classification of igneous rocks, which is one of the most practical and widely used method in petrology. Rocks are classified based on the proportion of ferromagnesian dark heavy minerals to non-ferromagnesian light silicate-rich minerals. Felsic rocks have rich in silica and alumina. It is mainly composed of light-colored minerals such as quartz, orthoclase, and sodium-rich plagioclase feldspar, making them less dense. Examples are granite intrusive and rhyolite extrusive. Intermediate rocks are balanced but still rich in plagioclase, 20 to 50%, and contains moderate ferromagnesian content. Examples are diorite intrusive and andesite extrusive. Mafic rocks are denser and darker, composed mainly of ferromagnesian minerals and plagioclase. For example, gabbro intrusive and basalt extrusive. Ultramafic rocks are the most magnesium and iron rich, often completely lacking feldspar and quartz. Examples are dunite, pyroxenite, peridotite, all intrusive. The terms sialic and sematic reflects their elemental composition and give insight into their behavior in crustal and mental processes. These distinctions are essential for identifying rock types in the field and understanding their geological origins and engineering relevance. Texture of igneous rocks. The texture of an igneous rock refers to the size, shape, and arrangement of its mineral grains, and it provides critical information about the rock's cooling history and environment of the formation. Phenolitic texture indicates slow cooling, typically in intrusive environments where crystals have time to grow large, as seen in granite or gabbro. Aphanitic texture results from rapid cooling, typically from volcanic eruptions forming rock-like basalt with tiny, barely visible crystals. Porphyritic texture reveal a two-stage cooling process. Initial slow cooling forms large crystal, phenocryst, followed by rapid cooling that forms a fine-grained ground mass. Glassy textures occur when lava cools so rapidly that no crystals form at all. Obsidian is a good example. Vesicular texture are formed when gases escape rapidly during lava cooling, leaving gas bubbles, cavities as seen in pumice or scoria. In civil engineering, texture directly affects mechanical properties. Coarse-grained rocks are usually stronger and more durable, whereas fine-grained or vesicular rocks may weaken over time due to weathering or porosity. Thus, texture analysis is essential for assessing rock suitability in construction, foundations, and aggregate use. Igneous Rock Identification Table. This table serves as practical guide to identify igneous rocks based on their texture, cooling history, mineral composition, and rock type. It distinguishes between intrusive, plutonic, and extrusive volcanic rocks, helping students understand how different geological conditions affect rock characteristics. Texture is the key diagnostic feature and is primarily controlled by rate of cooling. Coarse grain texture form from slow cooling deep underground, allowing large crystals to develop. Example, granite gabbro. Fine grained and glassy texture result from rapid or very rapid cooling at or near the earth's surface. Example, basalt and obsidian. Mineral composition ranges from felsic, high silica, light colored, to mafic and ultramafic, low silica, dark colored, which influences rock density, strength, and weathering behavior. A special texture like porphyritic two-stage cooling and vesicular gas escaping during solidification offer clues about rock's eruptive or intrusive history. The table links each texture and composition type to its corresponding intrusive and extrusive rock names, making it easier for students to identify and classify hand specimens or field samples. This classification is not just academic, it is essential for civil engineering. Rock type affects load bearing capacity, durability, excavation difficulty, and suitability for construction materials. Understanding these properties allows engineers to make informed decisions during site investigation and material selection. Self-assessment questions. At the end of the presentation, these are self-assessment questions. Go through each question carefully. Answer these questions based on understanding of the topic. Review any concept you are unsure about. The questions are: explain the process of formation of igneous rocks. Describe how the cooling rate affects their texture and classification. Describe the classification of igneous rocks based on silica content. Provide examples and discuss their engineering significance. Explain the difference between intrusive and extrusive igneous rock. Discuss how their formation affects their physical properties. Compare and contrast the physical and mineralogical characteristics of granite and basalt. How do these differences influence their engineering applications? Discuss various texture of igneous rocks and explain how each texture forms. Include examples of rock exhibiting these textures. Discuss the importance of understanding igneous rocks in civil engineering construction. Thank you for joining this lesson on engineering geology today. Hope you found this presentation informative. So don't forget to like and subscribe the channel Dr. A Classes for more engaging lessons on core subjects of civil engineering. Thanks.